All right, Ninja Nerds, so let's go ahead and finish up and wrap up acids and bases with our last calculation of the day. And that is going to be doing a weak base, strong acid titration. Our weak base being this methylamine here, and this strong acid being the hydrobromic acid. So again, what is this titration right here? We're going to be taking a weak base and doing it and reacting it with a strong acid. All right. So methylamine, if he's acting as the base, he accepts a proton. Who's the acid? HBr. So HBr is going to give up that H and convert this methylamine into the protonated form. So CH3 in H, he gains an H, 3 with a plus charge. And then you're going to get, what's going to happen? This bromine is actually going to get dissolved into solution as a spectator ion, right? All right, cool. So that's going to give us that part of the reaction there. And again, this is at equilibrium. Well, it's a reversible reaction. Not at equilibrium, it just means it's a reversible reaction. But it can have some type of dynamic equilibrium, right? First question, what is the initial pH? So we're doing that same thing where we imagine, what did we imagine? We have a beaker here. And what's in the beaker? Well, we're starting off with methylamine. So we're having that CH3 NH2 in here, and then what are we doing? We're taking and we're titrating in, we're dripping in slowly, all this purple stuff here. This is going to be the HBr, or the hydrobromic acid. We're dripping that in at a specific rate and a specific volume, right? But we want to know the pH before we add any HBr into the solution. So what does that mean? Okay, well, what is this guy? He's our weak base. What's the weak base formula? Let's write that out. OH negative is equal to the square root of the Kb multiplied by what? The concentration of our weak base, which is 0.175 molarity. Okay, and why am I using this one? Because we're starting off with our weak base. That's what we have in the actual beaker right now, before we added anything, before we titrated any HBr. So right now I have weak base in my solution, so I have to do the weak base formula. So let's plug everything in. So the hydroxide ion concentration, again, this is part A, this is for A, is equal to the square root of Kb. What's the Kb? 4.4 times 10 to the negative 4. Okay. And then what am I going to do? I'm going to multiply that by the concentration. What's the concentration? 0.175 molarity. If I plug this into the calculator, let's plug this bad boy into the calculator. 0.175 times 4.4, so I can e to the negative 4. And I'm going to square root this mofo. I get 0.0088. So again, out of this hydroxide ion concentration, I get 0.0088 molarity. Then what do I want? I want pH, but this is only going to give me the POH first, right? So POH is equal to the negative log of that. So again, negative log of 0.0088 molarity. What's that give me? Let's take the negative log of this, and I get, out of this bad boy, I get 2.06. So a POH equal to 2.06. But then I'm just going to do 14 minus that to give me my pH. So I'm going to do 14 minus 2.06 to give me 11.9. 11.9. And that should make sense. Why should that make sense? It should make sense because what are we starting with? We're starting with a weak base. So if you remember, that should make sense because why? The Kb is closer to 0. And the closer the Kb is to 0, the stronger that base is because it determines that ionization constant, right? So that should make sense. Cool. So we got A. Let's go on to B. What is B? What is the additional volume of acid that's needed to get us to the equivalence point? In other words, how much HBr do I need to add into this methylamine solution to get me to the point of where my moles of acid and my moles of base equal each other? What do we use for that formula? It's the same formula that we've used for the other two. M1, which is again the molarity of our methylamine, times the V1, which is the volume of our methylamine, equals M2, which is the molarity of our HBr, times V2, which is the unknown volume of HBr we need to figure out. What do? Molarity 1 is 0.175. Volume 1 is 25 milliliters. If I divide over, to get the V2 by itself, I divide over the second molarity, 0.150 molarity. What happens? My molarities cancel out. And what am I left with? I'm left with my V2, which is going to be in milliliters. Let's go ahead and calculate this out. So 0.175 times 25 divided by 0.150, I get about 29.2. We'll take that out one extra sig fig. 29.2 milliliters. So we'll take an extra sig fig, another number of uncertainty. So again, what is this number right here? 29.2 milliliters. That's the amount of volume that I need to add of who? HBr. So this is the volume I need to add of HBr to get me to the equivalence point, to where my moles of my HBr and the moles of my methylamine equal each other. All right, cool. C, what is the pH after adding 5 mils of HBr? Let's write out this. So let's do part C here. So again, let's write out this equation. Same thing, so CH3 NH2 plus HBr reacts, and again, this is in equilibrium, right? So we're going to have a reversible arrow here, and what do we get? CH3 NH3 plus Br negative. Fix my Br there. Okay, now what? What was the moles of him? We never really calculated that, right? Let's do that. So what do we need to do? We need to take the volume, get it into liters, so 25 divided by 1,000, which is 0.025, and then I need to multiply by the molarity to get me my moles. So I'm going to take 0.025 liters times 0.175 molarity, and I get 0.0044 moles. So again, I get 0.0044 moles there. For the HBr, okay, I added 5 mils of HBr. At what molarity? 0.150 molarity. So I need to get this 5 mils into liters. So 5 divided by 1,000 gets me 0.005 liters. And I'm going to multiply it by the molarity to get my moles. So I'm going to multiply that by 0.150. What do I get? Holy goodness, I get 7.5 times 10 to the minus 4 moles. Okay, what do we do? Same thing we've been doing. Which one of these is smaller? This one right there, right? So I'm only going to react 7.5 times 10 to the negative 4 moles of HBr with this guy, this 0.0044. So I'm going to react 7.5 times 10 to the negative 4 moles here. And what happens? All of this gets used up, and we're going to have a little bit left over here, right? So we take 0.0044 minus 7.5 times 10 to the negative 4. I get 0.0037 moles left of the methylamine. 0 of the HBr. But what happened? 7.5 times 10 to the negative 4 moles of methylamine reacted with 7.5 times 10 to the negative 4 moles of HBr and produced 7.5 times 10 to the negative 4 moles of this conjugate acid of methylamine. Okay, so what do we do now? I have moles of him, moles of him. That looks like I need the Henderson-Hasselbalch equation because it looks like I have a buffer. And a buffer is what? It's a weak, or in this case, this is a weak base and its associated conjugate acid. So again, I need to use the Henderson-Hasselbalch. So I need to say pH is equal to the pKa. Okay, well, how do I get pKa? What was I given? I was given Kb. I need Ka. What was that equation that we used? Kw is equal to Ka times Kb. So if I want to get Ka, I have to divide over by Kb. So let's do that real quick. What is that? So Kw is always a constant. 1.0 times 10 to the negative 14 divided by Kb in this case, which is 4.4 second e to the negative 4. And out of this, I get 2.27. So I get 2.27 times 10 to the negative 11. Okay, cool. So that gives me my Ka. But I want pKa because that's what the formula is, right? pKa plus log of the base, which is our base, this guy right there, over the acid. Okay. So if I have to do this, then what do I got to do? Let's go ahead and take the negative log of that, right? Because that's what pKa is. pKa is equal to the negative log of 2.27 times 10 to the minus 11. So pKa is equal to, let's go ahead and plug that in there. Let's take the negative log of that number. And I get 10.64. So my pKa is 10.64. Let's plug it all in. So pH, so continuing up here with C, we're going to continue up here. So we're going to take this part and continue up here. pH is equal to pKa, which is 10.64, plus the log of our base over the acid. What was the actual moles of our base? 0.0037. Remember, you can have it in molarity, but because I'm going to take the moles of my methylamine and its conjugate acid and divide them by the same volume, it's going to be the same ratio. So there's no need to put them into their volumes, put it into molarity, because if I put it into molarity, I'm going to have the same molar ratio if I were to just keep it into the moles. So I'm just going to keep it in moles. So 0.0037 is the moles, right? Because that's my base. And then over here is my conjugate acid, which is 7.5 times 10 to the minus 4 moles of my conjugate acid, because it's base over the acid. Let's plug all this in and see what our pH is. So we get 0.0037 divided by 7.5 second e to the negative 4. And then I'm going to log that puppy, and I get 0.693, and I'm going to add that to 10.64. So I'm going to add that to 10.64, and I get a pH equal to 11.33. So a pH equal to 11.33. Okay, so what happened then? I went from 11.9 to 11.33. Well, I didn't really add very much of HBr. I only added 5 mils, but it's still, what happened? The pH went down a little bit. So that's a good thing. So we're definitely showing some positive signs there. Okay, so we finished up. What was this one? This was the one for C, which is what is the pH at 5 mils of added HBr. Remember this one, pH at half the equivalence point, guys? Stick this into your cerebral cortex, that pH at half the equivalence point is always equal to the pKa, and our pKa in this case is 10.64. And this is always at half the equivalence point. So a simple one, quick, easy way to get some points here. Okay, so if they ask you what's the pH at half the equivalence point, it's 10.64, okay, which is equal to the pKa. All right, easy one there. Now let's do E. E is, let's calculate the pH at the equivalence point. Let's go over here and make some more room so we can do some more of this. Okay, so let's go ahead and continue. What was part E of this? It says, what is the pH at the equivalence point? What does the equivalence point mean again? We need to remember this. Moles of our base, in case of this reaction, which is our weak base, the methylamine, equals the moles of the acid. In this case, we're reacting with the HBr. Okay, so let's write out that equation again. What was it? It was CH3NH2 plus HBr yields what? We're going to get CH3NH3 plus and Br negative right there, right? And what did we say was the moles of our methylamine? The moles of our methylamine, when we calculated it, was 0.0044 moles, right? 0.0044 moles. If you don't remember how I got that, what did I do? I took the volume of our methylamine, which is the 25 milliliters, divided it by 1,000 to get myself 0.025 liters, and then what did I do? I multiplied it by the molarity, which was 0.175. So again, I'll show that real quick again, 0.025 liters. What do? 1 liter, I'm going to multiply that by 0.175 molarity, and then I get out of this 0.0044 moles. Okay, so that's how I got that one. Okay, so now that we know how we got that one, HBr, what do we say? At the equivalence point, this concept here, okay, this, right? This guy right there, moles of acid and the moles of base are equal to each other. What do I mean then? That means that this guy has to be equal to him also, 0.0044 moles. Because that's what the concept says. At the equivalence point, these two are equal to each other. What do? I subtract whichever one's lower, but they're both the same. So if they're both the same, what happens? I have none of him, I have none of him. But 0.0044 moles of the methylamine reacts with 0.0044 moles of the HBr and produces 0.0044 moles of our conjugate acid of methylamine, which is the CH3NH3+, which is a weak acid. If it's a weak acid, what is the formula for a weak acid? A weak acid formula is H3O plus is equal to the square root of Ka. In this case, what did we say was the Ka? The Ka is 2.27 So 2.27 times 10 to the negative 11, and we calculated that by taking Kw divided by Kb that they gave us in this reaction, and we're going to multiply that by the concentration of my weak acid here. Well, we don't have it yet. We only have moles. Okay, well, let's see what it is. 0.0044 moles of this guy. Well, I got to put that over the total volume of the solution right now because that's molarity. What did I have previously? Well, previously I had 25 milliliters of this guy. Then what did I do? I had to add the volume to get me to the equivalence point. What was the volume that took to get me to the equivalence point? It was 29.2 milliliters. So now what? Down here, I should have the volume that I started with, which was 25 mils. So I'm going to put 0.025 liters. And I'm going to add that to the volume of HBr it took me to get to the equivalence point, which was 29.2, so it's just 0.0292 liters. And that's going to get me my molarity. So let's go ahead and get that number right there. So if I take 0.0044 and I divide that by 0.025 plus 0.029, I am going to get 0.081. Let's write that out, 0.081 molarity. Let's plug that in right there. 0.081 molarity. And now what am I going to do? Multiply it by that guy. Multiply it by my Ka. So 2.27 second e to the negative 11. And then what am I going to do? I'm going to take the square root of that number. And that's going to give me 1.36 times 10 to the negative 6. So again, what was my H3O plus concentration? It's equal to 1.36 times 10 to the negative 6 molarity. What's the next thing? I got to get pH because that's what they wanted. They want the pH. Well, pH is equal to the negative log of this guy. So pH is equal to the negative log of the H3O plus concentration, which is 1.36 times 10 to the negative 6 molarity. So this pH is probably going to be somewhere around 5 point something. Let's go ahead and plug this in. So we take the negative log of that answer, and I get 5.9 approximately, right? So about 5.9 for the pH. This should make sense. Why? Because if you remember, we talked about it briefly in the titration curve whenever we did the titration with, this case it's a weak base and a strong acid, but the other one we did a strong base with a weak acid. And we said that the pH whenever, at the equivalence point, whenever you're reacting a strong base with a weak acid, it should always, the pH at the equivalence point should always be greater than 7. Well, in this case, if you're reacting these guys, if you're reacting a weak base with a strong acid, the pH at the equivalence point should always be less than 7 because you have a strong acid here. So it should be bringing it below the equivalence point, at, below the neutral point, so below 7, in this case 5.9. That's good. So that means we're on a positive route here. So again, that's how you get that answer. Let's do the next and last one. What is the pH of the solution after adding 5 milliliters of HBr beyond the equivalence point? Okay, let's write this equation out again. CH3NH2 plus HBr yields CH3NH3 plus Br negative. And again, what was the moles that we started with here? We started with 0.0044. And HBr, we got to figure out, okay, what volume are we adding? Well, it took us, what volume to get us to the equivalence point? It took 29.2 milliliters to get us to the equivalence point. But then we added 5 mils beyond the equivalence point. So that means it was 29.2 plus an extra 5 milliliters. That's 34.2 milliliters. So in other words, I have to take 0.0342 liters, because all I did is just divide 34.2 by 1,000, and multiply it by its molarity. Well, HBr molarity is 0.15, so 1 liter, 0.150 molarity. This is going to give me the moles. So if I take that number and I go ahead and multiply this by 0.150, what do I get? I get 0.00513. Let's write that in there. 0.00513. So I get in this 0.00513 moles. Cool. Now what do I have? I have to subtract the one who's lower in amount, right? Which one of these is basically our limiting reagent, the one in the lower amount? The methylamine. He's going to run out first. So we're going to subtract 0.0044 here, subtract 0.0044 moles here. Here we're left with 0. Here we're left with what? Okay, let's do that. Minus 0.0044 here, and we're going to get 7.3 times 10 to the negative 4. So I get 7.3 times 10 to the negative 4 moles here. But again, 0.0044 moles of the methylamine reacted with 0.0044 moles of the HBr and produced 0.0044 moles of the methylamine conjugate acid, the CH3NH3+. Okay, so now what? We remember this whenever we did this with the weak acid strong base titration. We were left with a certain amount of a strong base and then the weak base. Well, look what we have now. Now we have a little tug of war between the strong acid and the weak conjugate acid. What did I say before? He doesn't matter. We don't care about him. We care about the strong one. We only care about HBr. So he's negligible. We don't care about him because he's going to determine more of the power of the pH. So then pH is equal to the negative log of the H3O plus concentration. Okay, well this isn't in concentration yet, I just have moles. So now what do I have to do? I have to take 7.3 times 10 to the minus 4 moles and put that over the total volume that it's taken to get me to the end volume of the solution. What was the original volume of HBr? The original volume of HBr was 25 milliliters, which is 0.025 liters. Then the volume that it took to get me to the actual equivalence point, the amount of volume I added for HBr was what? It was 29.2 milliliters. But then I added an extra 5 milliliters to it. So what's that? 29.2 again plus 5 gives us 34.2 milliliters, which is 0.0342 liters because I just divide by 1,000, right? So this is the total volume of the solution. So now I'm going to take this 7.3 second e to the negative 4 and divide this by the addition of these two volumes here. And when I do that, guys, I get 0.0123, let's write that out, 0.0123 molarity of who? HBr. And then what do we do here? Since he's a strong acid, we just take pH is equal to the negative log of 0.0123 molarity, right? And then I'm going to go ahead and take the negative log of this, guys. And what are we going to get out of this? We get 1.91. So that looks pretty good, 1.91. All right, so this should make sense because why? Because we kept adding more acid beyond the equivalence point, so we're starting to just work it completely into just acid at this point in time. All right, now that we've done all the calculations, let's go ahead and take a look at the titration curve over here in the corner. Okay, so finish up here with the titration curve and what it's going to look like, and then we'll label it quickly. All right, so it's going to kind of follow the same trend that we followed with all the other ones. So in this case, what are we starting with? We're starting with methylamine. Methylamine, we said, what was the initial pH of it? It was about 11.9, so we're going to say that's about here. We're going to go with just about there, approximately. So if we work this way, his pH is going to be here, right? But then we're starting to add, again, what's on the x-axis? The volume of HBr that we're adding over time. So then let's say that we get to the point where we add a little bit of volume here. We add about half the equivalence point, right? So we get to about half the equivalence point, which is half of 29.2, half of 30 about, which is about 15 mils. So we get over here to about 15 milliliters. We're going to start noticing this little like drop a little bit. We're going to notice a little drop. And then what's going to happen? We're going to get eventually to about the equivalence point, which is about 30 mils. So let's say it's working this way. And then what happens? It starts dropping significantly, right? So it starts dropping, and then what happens? Eventually, almost all of the methylamine is gone, and almost all of it is converted into acid at this point in time. So it's going to kind of look a little bit something like this. So again, a little bit of a, let me do it a little bit better here. Again, it would kind of take something like this right there. Okay, that's going to be this titration curve. And it should just look, again, starting up here with not as high up to 14, around 11.9. And as we get to about 15, we'll notice this little half equivalence point. And then as we get to about 30, it should start making this crazy inflection point to get us to the equivalence point. So our equivalence point is about, we'll say, about right there. And if we work this over here, what do we get? It's below 7. So that means at the equivalence point, which we said whenever you're doing a what? A weak base, strong acid titration, it should always be what? Less than 7. And in this case, it was about 5.9, we said, which is good. Then we said at about half the equivalence point, which is about right here, when we did that, half the equivalence point is equal to the pKa, right? And the pKa was about 10.64. So it's going to be a little bit less than 11.9. So it's going to be a little bit less. So if I were to show it, you should kind of show it actually just a little bit more, kind of like this here, maybe, boom, like that. Okay, so again, just a little bit less. Let's say that that was the 11.9 point, which was the initial, and then it should drop a little bit over here at half the equivalence point, right? So about 10.64. So right there is about half the equivalence point, and then eventually, once all the methylamine is gone, we just convert it primarily into just acid at this point in time. So it's going to have some HBr and the associated conjugate acid. Okay, so that's what the titration curve would look about, and whenever you're looking at a weak base, strong acid titration. I hope this all made sense, guys, and I hope that it helped. All right, Ninja Nerds, have a good one.